So same problem here as well. Let's say if there are here there were four four variables, like right? Volume, horsepower, weight, and speed. There are four variables. How many plots, unique plots there will be? How many unique plots I will have to uh, plot in order to understand their correlation? Six. Yeah, correct. So six will be volume versus horsepower, volume versus weight, volume versus speed, horsepower versus weight. Sorry, volume versus weight. Then, horsepower versus weight, horsepower versus speed, weight versus speed. Uh, Anything is left? No. Okay. So there are six graphs that I will need to plot. Correct. But let's say there are 20 parameters. How many graphs I would have to plot? That would be 20 uh, combination 2. So what the value will be? 20 into so easiest way to calculate is first see how many values are here. 2 means 2 into 1. 2 into 1 and then 20 into 19. So this comes out to be 190. Okay, so 190 plots I will have to do for 20 features. So you can understand, like if there are 100 parameters, then it is really unrealistic to plot all. So we come up with a solution, and that solution is called come up VIF. So VIF stands for variation inflation factor. It's called as variation inflation factor. So in order to check if x1, x2, x3, x4 are independent, what we will do is we will create models like this. So x1 and x1 against x2, x3, x4. So we will try to predict x1 using the other features. Okay. So if we want to check if there is dependence or not, in order for this to be independent, this model should give good result or bad result. Yes. So only if there's a bad model, then only we can say that they are independent. So the ideal scenario will be a bad model, and good model implement that it is against the scenario, so it implement that there is a dependence, or we can say it implements that features are not independent. So, but in order to even tell if it is good or bad, we will need to come up with a metric. So, which metric we had used for SLR? For SLR, which metric we used? Yes. No, no. In order to check, so once we come up with the best model, how did we evaluate that model? R square. So we came up with the R square. So in this case, uh, so in this case, lower R square is better or higher R square is better? Lower R square. So just we in case of this, instead of using R square directly, we use VIF, which is 1 by 1 minus R square. Okay. So tell me, VIF is directly proportional to R or indirectly proportional, inversely proportional square. Okay. So let's yeah, actually it is directly proportional, but easiest way is to put the values and check, right? So if my R square is equals to 0.5, VIF will be equal to 1 by 1 minus 0.5, which is 1 by zero point 0.5, which is 2, right? If R square is equals to 0.9, then 1 minus 1 minus zero point 0.9, which is equals to 1 by 0.1, which is equals to 10. So with increase in R square, there is increase in VIF as well. Correct? So they are directly proportional. So VIF, if it is less than 10, then we assume features are independent. Okay. And if VIF is greater than 10, then we say assumption is not satisfied. Okay. Clear? So what we did is we we created the, so in order to solve the in order to check the assumption, we are creating another multilinear uh, regression model, but instead of x and y, we are creating the models among the features itself. Okay. And with those models, we will come up with a score for each model combination. So for these four parameters, so there will be x1 against versus x2, x3, x4. Then we will have model like x1, x2 with x1, x3, x4. Then x3 with x2, x4, and x1. So these models we will build. We will check the VIF score. If VIF score is less than 10, then we will say, okay, our features are independent of the independent of each other. If VIF is greater than 10, then we will say the assumption is not satisfied. Clear? Okay. Now, uh, in case this assumption is not satisfied, let's see what is the resolution. Okay. So the resolution here is that let me just take the VIF scores that I found. Okay. So let's say for the volume, I have 638. For weight, 640. Horsepower, 19. SP, 20. Okay. Now I can see that all the values are higher than 10. So, uh, so definitely there is the features are not independent. I found that features are not independent. So what we will do is we will uh, obviously first we will check the correlation. If there is any obvious correlation between any parameters, then out of that we will so so uh, let's say from the correlation we found that there is a dependence between volume and weight, and there is dependence between horsepower and SP. Let's assume that we found this correlation after plotting and after doing the after finding the correlations. Once we do that, then we will build the models only with these parameters. So with volume and horsepower, volume and speed. Then third is uh, weight and horsepower, and weight and speed. So what we will do is we will take only one of these parameter and only one of these parameters. Clear? And then we will build the model. Then we will check the R square score, and then we will use that particular model. So what we are doing is, out of these dependent variables, we are dropping one dependent variable. But which one to drop? In order to choose that, we will have all the combinations. Then we will build the model with all these four possible combinations. Whichever works best, keep that and discard the rest. Clear? So let me just take that example of square meter and square feet, right? So in order to improve my model, I will need to drop one of these. The easiest way is to drop one of these because they have dependence. I don't want that. I don't want that. So uh, as there is a dependence between these two, what is the obvious solution I can do is drop one of these. Okay. Just keep one parameter and you will be able to resolve the problem. Correct. So if I drop square meter, I just keep square feet, then my this is the uh, model I get, and this works well. Correct. So here also, if there is dependence between volume and weight and horsepower and speed, what would be the obvious resolution? Just keep one parameter from volume or volume and weight, and one parameter from speed and horsepower. Right. So either you drop horsepower or you drop speed, or you drop volume or you drop weight. Either one of so out of this pair, volume and weight, you keep either weight or volume. Don't keep both. Same from horsepower and speed. Don't keep both. Keep either one of them. Huh. So, Yeah. So first we plotted all the, so first we saw from the correlation, from the, uh, so from the correlations, first you find the correlations for all. Ha, yeah, where there is a dependence, high dependence pairs. And then we will do this. So let me just show you that. Yeah. So you will make a graph like this. Let's say this is the scatter plot with correlation coefficient. Okay. Now check here. You can find, so in order to read this graph, uh, check these values in the middle. Okay. And draw kind of a perpendicular. Whichever is the intersection, that will be the graph for those particular variables. So this is weight versus speed graph. And for the same, if you look diagonally, it will give you the correlation. Okay. Now see here and find, check the combinations for which there is very high correlation. So it is this one is there, then this one is there, then any other one. Yeah, so what we did is, for volume we have plotted this. So if you check this particular data, it is volume versus weight. So this is weight, this is volume, sorry, this is weight, this is volume. And diagonally if you look, it will give you the correlation. Python, yeah, that we will see how to generate this. But you will do graphs like this, and then you will check, and then you will find the correlations. So you can see one here, which is SP and HP. And then you, if you look diagonally opposite, then this is the correlation. Clear? So then you will find the pairs, and then once you find the pairs, then out of that, which one to choose. Now in look in here, I know now volume and weight has dependence. Okay, but should I keep volume or I should keep weight? Which one I should keep? Because there is no obvious reason that I should keep weight over volume or volume over weight, right? So in order to check that, I will build all the models with all combinations, and then out of that, whichever is best, I'll keep that. R square value, I will keep that. Whichever is a higher R square value, I'll keep that. I'll discard the rest. Is this clear? Rest we don't need to use. So we will use only that model which has higher R square. No, no, no. Okay. Mm. So see, dependency we check when we did the test. Test we did for the features. Okay. Not the output. Okay. Now we want to now we found out that there is a the all variables are not independent, or the features are not independent. Then we thought, okay, what could be the resolution? So we got VIF values like this, which indicate that there are some features which are dependent, correct? Because VIF value is higher than 10, which indicate that the features are not independent. Then we saw the correlation and saw like then we checked which pairs has higher correlation. We isolated those pairs. We found out the pairs. So then we found out that the pair volume and weight and HP and SP has higher correlation. So they are not independent. Correct? Now I need to choose one of these, either volume or weight, and I need to choose horsepower or SP. Correct? So in how many combinations I can choose? I can choose volume with horsepower. I can choose volume with uh, speed. I can choose weight with horsepower, and I can choose weight with SP. Correct? Okay. So now, uh, out of these, which is the one I should use? How do we determine that? So we will build all these models, check the R square. Whichever has best R square, we will keep that. Others we don't need. Is this clear now? So we found out the pairs, okay? But we don't know should we keep volume or weight, or we should keep horsepower or speed. We don't know. Now we want to find out that I should keep volume or I should keep weight, or I should keep horsepower or I should keep speed. So yeah, yes, correct. So if R square will vary between 0 to 1, if R square is closer to 1, then that model is good. So keep that model. So for example, if this gives you 0.9, whereas in this gives you 0.8, keep this one. I mean, use this one for your prediction. Clear, no? Any doubt? Shall I explain this again? Yes, correct. So, so first we started with understanding if the assumption is satisfied or not, right? So that's why we calculated the VIF score. VIF score, how we calculated? We build the model between the features. So x1 against all other features, x2 against all other features. Like that, we build the models, and then we calculated the VIF score, right? Okay, just a second. Yeah. Then we got the VIF score something like this. Now what we said, if VIF score is greater than 10, that means there is certain dependency between the parameters. Correct. So then we saw that there are the VIF score is greater than 10 because it's 638 and things like that. So we now know that there is obvious dependence between the features. Then we found the pairs which has high correlation. Okay. Once we have the pair, Now we need to eliminate one of that. So if I have volume and a weight pair, I need to eliminate one of the feature from here. I had four features earlier: volume, weight, horsepower, and speed. No, no. Our assumption is that features should be independent of each other. Because if there are dependent pairs, so think of it like that square feet and square meter example. We just want one of these. We don't want both, because if we keep the both features, then we will have the wrong interpretation. So similarly, if we keep both volume and weight and SP and HP, if we keep both from this, then we will have uh, lesser um, mm, interpretation will be wrong. Is this clear? So as these two are dependent, we don't want dependent variables, so we will eliminate either one of these. Now, how do I choose? Should I eliminate volume, or I should eliminate weight? In order to determine that, you form all the pairs first, keeping all the volume first, and then weight, and then check which is performing the best, and then you keep that pair, and yeah, you keep that, you use that as a model. Got it? No confusion now, right? So yeah, that's what we do. Mm. So let's summarize first what all we learned. Okay. Let's summarize what was our assumption, what is the impact, and then of that particular assumption, and then test to determine if that assumption is satisfied or not, and what is the resolution. So our first assumption was, what was our first assumption? Yes. Yes. So our first assumption was all features should be independent of each other. The impact was in prediction or interpretation? So remember that uh, equation we had. Yes. Yeah. So we can predict using this equation, but because there is nothing mathematically wrong, but we can't interpret using that equation. So the impact is in interpretation. What tests we did? Just now we saw the test. Yes. So VIF, and then we also did the plots. Okay. So what was the resolution? Select the best subset selection. So select the best subset that you have, and then you can delete the other features. Correct? Then what was the second assumption? Correct. Features and errors should be independent. So the problem was with the prediction or interpretation? Prediction. Correct. And how did we do that? How did we do the test? What? Mm-hmm. The error versus. Yes. So either error versus feature you will plot, or so first plot with plot error versus y cap. If there is, if you find any kind of dependence, then you plot with each feature, right? What was the resolution we discussed? That we did in the first, for the first assumption. If they were dependent, we discarded. But in the second, we discussed that we will use the transformation. Yes. Like log, exponential, or square. Then our third assumption was error comes from normal distribution. With mean 0. The problem was with interpretation or prediction. Yes, interpretation. In order to test, what did we do? Yeah, histogram. And another one was QQ plot. For this resolution, yes, same thing, transformation. Then the fourth one is, we say that it should have homoscedasticity. The problem was where with the variance of the errors changing. Problem was with the prediction or interpretation. Prediction, correct. And what were the tests that we did? So we plotted error versus y cap. Okay. So with this one plot, you will be able to determine both. Yes. Yeah. And then the resolution is here also is a transformation. Is there any doubt in this? Yeah. Yeah. So first you will calculate the VIF score. Okay. VIF score will tell you that features are dependent or not. Okay. If you found out that VIF score is greater than 10, then that will imply that your features are not independent. Now let me take one example. So let me just take. mm, okay. Uh, need one example. Let's say y depend on x1, x2, x3, x4, x5, x6. Okay, right? So we have already found VIF score. So let me write VIF score for each one of these. So let's say 2.1, 2.9, 2.6, 91.4, 21.7, and 75.8. Okay. Let's say these are the VIF scores. Correct? Straight away select these features. Keep all these features straight away. Because VIF score is less than 10. Okay. First thing you do is keep all these features. Okay. Now it will tell you that these features has some dependence. Okay. Correct? Because VIF score is high, this feature has some dependence. So uh, so you have already selected these, correct? Don't worry about this now. Now out of this you need to choose, correct? So then you create a model with x1, x2, x3. uh, so create subsets like this: x4, then x5, then x6, like this. Okay, check the r square score, and then whichever is the best you keep that. Okay. There is another way to do it. Instead of directly going for this, what you can do is you already have selected these three. Okay, don't touch it, don't do anything about it. Now here again, find the subsets and make the models. So for example, x4 with x5, x6. Okay, then x5 with x4, x6. So like this, make model, again calculate VIF score for these. Then it will tell you that if they have dependence. If they have dependence, just choose one of the ones that will give you. Then again do that: x1, x2, x3, x4. I don't know why this is happening. Anyway, so we calculated that. Then so you found that x1, x2, x3. Okay, these you have already selected. Now you need to select from x4, x5, x6. Correct. Build the models from all the combinations for this. This will tell you which, like if two of them are dependent or all three of them are dependent or how it is. Okay, from the VIF score. Then you make the models like this: x1, x2, x3, x4, then x1, x2, x3, x5. Okay, you have already selected this. Out of these, choose just one each time. Now for this, check the R square. Whichever has the highest R square, choose that model. Is this clear or have I confused you more? No, no. Okay. Okay, so yeah, the theory part till now, like all the theory part is covered. Now there is just one more concept that I want to tell, and that's just so let's take 10-minute break and then we will see that part. Yeah, lot of theory today. So let's take a break for 10 minutes. Let's meet at it's 9:55 now. So we will meet at 10:05. Okay. Okay then. We'll see you at 10:05. Okay. Hello? Hello? So that's why two metric. Wherever VIF, always it should be less or R square should always be high. Okay. So there is one more part that I just want to how to detect outliers. So one method of detecting outliers we have already seen. Do you remember that method? There was one plot that we saw that using which we can determine outliers. You remember the box plot? We said that anything outside this box plot is outlier. Yes, correct? Yeah, we have already seen box plot, and what we saw told is whatever is outside this box plot is an outlier. But there is a limitation of box plot that it will only consider one variable or one feature at a time. So think about it, okay? Let's say there is a person. If I say there is a person with height 6.2 feet, right? Would you be surprised? Like, is there any like even Mahesh? I think Mahesh, you are 6'2", right? So this is not surprising. There are many people with height 6'2". Okay. If I say there is a person with weight 49 kg, this is also not surprising because there are a lot of maybe let me say 40 kg. Okay. So let's say there is one person with 40 kg. Even this is not surprising. But if I say there is a person who has 6.2 feet height and 40 kg weight, then that is surprising, right? Because we can't imagine a person with 6.2 feet height and 40 kg weight. It's very uh, unrealistic. So sometimes independently these results are not outliers. So this is not an outlier, this is not an outlier, but combined it is outlier. Okay? So independently they are not outliers, but combining both uh, will be an outlier. So with multiple variables, uh, the so with multiple variables, box plot can't help. So that's why we want to come up with a better metric or better way of finding outliers. So sorry, let me just take one example. Let's say this is our data. Okay? Then let's say I fit the line like this. Okay. Now let's say I added an outlier. Okay. Wait, let me- Now let me say that I added an outlier somewhere here. Okay. Now, what adding this new data, what it will do to this fitting? Would this move the fitting? Correct. So it will either move it to the right or left. Correct. So if it moves, let's say this is a new fitting. So what it will do is it will shift the line, or maybe if not this much, but it will have certain impact. Let me just say that it moved the line here. So this is my new fitting after adding outline. Now let's say I added a few more outliers like this, maybe one or two more. Okay, outliers like this. Then again it will shift the fit a lot. So you shifted from here. This was your actual fit. From here you shifted till here or here, right? So this is without outlier, and these are with outliers. So in the presence of outliers, model is significantly impacted. So if that is the case, what is the best way to find out the outlier? So the best way to find outlier is delete one data at a time, then measure the change before and after the deletion. If the change is significant, then it implies that data point is an outlier. If change is mild, then data point is an inlier. So let me just tell you what I mean. So let us take that example. Let's say our y is mileage volume we have HP, weight, and SP. Okay, so this is our x1, this is x2, this is x3, and this is x4. Okay, let's say we have so this is the data. Just okay. So let's say this is the data. Okay. Now the data there are 81 rows, 81 rows like this, and 5 columns. So these are the 5 columns: 1, 2, 3, 4, 5. Okay. This is the total data. Clear? Let me just write it. MPG, volume, HP, weight, speed. We have data like rows like this. It has certain data, let's say 24, volume something like 78, anything like 300, weight 4000. I'm just putting the random values, but it has data like this. Okay. Just like we have an Excel sheet. It has 81 rows, 5 columns. Now, initially, first you build the model y bar, considering all the data, all 81 columns, all 81 rows, 4 columns, because this is your y. So you will be building the model with these 4 columns. Okay. So then consider all with 81 data points and 4 features. Then let's say your y bar is 1x1 plus 2x2 plus 3x3 plus 4x4 plus 5. Okay, let's say these are the values that you got after considering all 81 data points and 4 features. Okay, any doubt till here? So then what you do is delete the first row. Okay, delete this first row and remaining 80 data points. So minus 1 the first row, you delete the first row, and after deleting first row, again fit the model y bar on 80 data points. Okay. Delete the only the first row, and on 80 data points you again fit the model. Then maybe you will get the values like this: 100x2, then 0 3x3 4.9 or something like that. Okay. Now you can see that the value, the uh, parameters are not too different. If the parameters are almost same, then you can say that your data is not an outlier. So that particular row is not outlier. Now let's say, now restore the first row and delete the second row. So delete second row, restore first row. Then again build the model. And now let's say your values are like this. Or maybe I'll just give a very high value. Okay. Then you can see clearly that the parameters are hugely impacted. Okay. If this is the case, then count this as an outlier. Okay. So what I mean is, delete one data at a time, then measure the change before and after. How you will measure the change? In order to measure the change, just calculate the distance. The distance will be equal to square root of, so let me just say that this is 2, 3, 4, just for the ease of calculation. Let me just take 2, 3, 4, 5 and 6. Okay. So this was my initial model. This is my final model. So 2 minus 1 square plus 3 minus 2 square plus 4 minus 3 square plus 5 minus 4 square plus 6 minus 5 square. This is how you will calculate the distance. Sorry. Parameter here minus the the value of the parameter here minus the value of parameter here, and square of that, and take the square root of the entire value. This comes out to be a square root of 1 square plus 1 square plus 1 square plus 1 square plus, so minus 5 is 1, so again 1 square, so 1, 2, 4, 5, the square root of 5. Now this is called, this is how you will sorry, so this is how you will measure the distance. Now we need a threshold to determine we can how much after how much threshold we can consider it as an outlier, and so outlier or not. So that is called Cook's distance. This is the same author who gave this method. So we use this Cook's distance. So the distance is like this: 3 into k plus 1 divided by n, where k is number of features and n is number of rows. Okay. So in our case, it is 3 into 4 plus 1, because there are 4 features, divided by 81. Comes out to be 15 by 81, which is something like 0.19 something. Okay. Is this clear? So this distance that you calculate, so this is with the entire all the data set, correct? This you calculated after deleting one data set, one data. Now then you calculate the distance, so with all data and after deleting. You calculate the distance between these two. Once you calculate that distance should come less than this value. Then that's not an outlier. If distance is more than this value, then it's an outlier. Okay, understood? Okay. So any doubt in this theory? I know it's quite intense, like this particular. So let's say you have four features. If you have four features, you will have four parameters like this. Five parameters, beta. So you remember that equation, alpha 1 x1 plus alpha 2 x2 alpha plus alpha 3. So let's say your initial y is alpha 1 x1, alpha 2 x2, alpha 3 x3 plus alpha 4 x4 plus beta. Okay. And let's say after deleting first value, let us call it y minus 1. Okay. So deleting, we are deleting the first value. After deleting, let's say you got parameters gamma 1 x1 plus gamma 2 x2 plus gamma 3 x3 plus gamma 4 x4 plus, let's say, some eta. Okay. I'm just get, taking the random values for the parameters. Okay. So what I just want to imply that after deleting one row, there will be some change in the parameters. Now calculate the distance. That would be equal to square root of alpha 1 minus gamma 1 square plus alpha 2 minus gamma 2 square plus alpha 3 minus gamma 3 square plus alpha 4 minus gamma 4 square plus beta minus eta square. Clear? Now, this distance, so the distance that we calculated, let me call this some value. Uh, okay, let us call it distance. So this distance should be less than 3 into k plus 1 divided by n, where k is number of features and n is number of rows. Now, yes, yes. So after deleting each, so what we will be doing is we will delete one row at a time. Then the measure the change before deleting and after deleting. Okay. If change is significant, then we will consider that as an outlier. If change is mild, then we will consider that as inlier. We don't do this manually, we will do it using Python itself, but just understand the theory. Clear? So any doubt in this theory part? Any doubt in the assumption? How do we test it? How do we do the resolution? And any doubt in outliers part? Okay. I know it's little intensive in terms of the theory, but okay. So I have posted two files in the uh, our WhatsApp group. So can you download those two? So we will just quickly see how to write the code for it. Then we will be done for it. So there are two files. One is multilinear regression notebook and another is the cars.csv data. I did that. Okay. Mahesh, let me know once it's done. Right. Okay. So skim through the just skim through it first. We'll discuss. Just skim through this. You will understand most of it, but then we will discuss. Huh, we will discuss. Firstly, we are just importing all the libraries, pandas for to import and pre-process the data. Matplotlib is to plot the graphs. Seaborn also we have seen already. This is to plot the graphs. Stats model to uh, build the model. Uh, so you see here we are importing the particular uh, plot function as influence plot, and we are importing this that model dot formula dot api, which has all the model ols, like whichever we require, that as smf. Okay, and then we will import numpy as mp. This is to use the mathematical function. Now here we will first read the data. We are using CSV, read CSV. Here we will pass the name of the file. Make sure that name and notebook are in the same folder. Otherwise, you will need to give the absolute. And then cast.head. This will print the uh, first few values, the data. Then we found out the correlation. So we found out the correlation between all the parameters. So HP versus HP will obviously be 1. Then the correlation between mileage and HP is this much. So like that, we found correlation for all values with all other values. Okay. Now from here, I can see that this particular value is high, almost 97%. And then this particular value is high, which is 99%. Now I thought, okay, yeah. Oh, okay. Sorry, sorry. Okay. So here we imported all the libraries. Then we read the data. Okay, and then we found the correlation. Now we uh, found the. You have read the cars data, right? And I have stored it in the variable cars. Now if I do cars dot corr and give the brackets, then it will give me the correlation. That's all. So then once we get the correlation is nothing but it is giving you the like how much is the how much this particular how much mpgs will change with change in hp. Okay, so once you have the correlation, now I can identify that this particular value between sp and hp is almost 9, so it's 97%, and between volume and weight it is 99%. All other values are quite like not too small, but yeah, small. This is slightly high but not that high. So yeah, so these two values are very high. So but this is also uh with y, this is not with other what to say, other feature. So that's fine. With whatever is with mpg, that's fine. So we got this value which is very high and this value which is very high. So now what we will do is we will plot those values first. So I'm using the sub. So this is clear, right? The figure size is 10 comma 4. So my x will be uh, 10 centimeter, 4 will be, y will be 4 centimeter, so things like that. And then so that will be my figure size. Then I will be using subplot. Subplot takes 3 parameters. So whatever is the number of row, whatever is the number of column, and out of those total figures that you are gonna plot, which number of figure it is. So what I'm saying is, take one row, two in that there will be two columns, that means two figures. Out of that, first figure will be this figure. Okay? So this figure is scatter plot between car's volume and car weight. So I'm just giving the color red to the points in the scatter plot, and I'm just giving the label that correlation is 99. How I found that? With this correlation that we calculated. So the correlation between volume and weight, correlation is 99. Okay, and then best means it will find the location where is the minimum overlap. So then we will calculate the second subplot, which is HP versus SP. Okay, and then we have already got the correlation here. So then we'll plot the graph. Once we have plot the graph, we will, yeah. So now we can see that even in the graph, we can see that it is very highly correlated. This I'm just plotting the info to check non-null values and also the data type of these features. This is pretty straightforward. It is to check the null values. There are no null values, so we don't need to bother. Clear till now? Any doubt till here? No, no. Okay. So yeah. Okay. So then we will whatever the correlation we plotted, right? So we can plot the heat map for it. Heat map will just give us a color gradient according to the values. In order to get the, you can use anode is equals to true to get the actual values as well. Anyway, till then, till it's running, we can just go through it. Okay, so this is the heat map. It will just give us a perspective. So black values indicate low or no correlation. Uh, white values indicate the high correlation, and then the red are intermediate. Then this is a scatter plot between along with the histogram. But you know, when we will have higher and higher number of features, this this will not be that much of importance, because anyway we can't plot for 100 features the scatter plot. So yeah, so but this has all the information that you need. This has all the scatter plots along with all the histograms. This has all the information that you will be needing. Then is this clear till now? Any doubt? That's the heat for the correlation matrix. Yeah. So heat map is for the, Okay, yeah, heat map is just to understand the correlation. That's all. Okay. So then, yeah, that is because of the matplot in it is not getting. Yeah, just do plt dot show. Will show, but yes, need. Yeah. So, okay, just do plt dot show. Mm. Uh, yeah. So where were we? Yes, heat map, and then I will note. Okay. So then it will give you all the corresponding values for the correlation. This is just to understand. This comes from the idea of the thermal graph, just to get you an idea. Okay, it- because you see all the whites you can clearly identify easily, whereas with these correlations, where the correlation. Okay, now see here, it's little difficult to identify which one is the high, but here you can clearly, even without the numbers, you can clearly identify, okay, the SPHP, volume and weight. These ignore the diagonal, because diagonal will always be 1, because it's with the HP, MPG, then it will always be 1. If you just ignore the diagonal part, just look at any one side of the diagonal, you can see that these two white are there, which has very high correlation. So it just help you to easily understand the pairs which are, have high correlation. That's all. That's the only use of this. Otherwise you can also determine the same information even from these numbers. Clear? Okay. So then these are the scatter plots between, this is called pair plot actually. So this is called pair plot. It plots all the features and all the variables with all other variables, and on the diagonals there will be histograms. Now we will for now prepare the first model. Now first model, so we will import this library. We have already imported on top, but importing again. Then once we import that from SMF, SMF is the alias, use that, import the function OLS. OLS stand for ordinary least square. Then once you import, call this function. Now what you are doing model against, this is your y is your mileage, and against all the other features, which is weight, volume, SP speed, and horsepower. Make sure that you write the feature name as it is. There should not be extra spaces. It should not be uh, changed. If it's capital, you shouldn't make it small and things like that. Okay, it should be exactly as it is. So once you do that, uh, also pass the data, which is cars data, and then just do dot fit. Once you do this, your model is ready. You can check the R square value, which is 0.77. You can also do model summary. In model summary, look at the, you can check the dependent variable R square value. You can just check these intercept values. There is also uh, one value, that is p value here. Okay? If p value is high, then there is something wrong here, because here here what is the, okay, so this is your y predicted, right? When you calculate the p value, your your null hypothesis is that your a1 is, so let's say you're calculating p value for the feature wt. Okay, then you are assuming that your a1, which is the parameter, multiplication parameter for your weight, is 0. That is your null hypothesis. If that has very high probability or very high p value, that means there is a problem. That means all the all the parameters multiplied to weight will be 0. That means your y prediction will not have any zero, anything, um, any component of weight, basically. So that is not something we want. So if there is high p value, that means there is some problem. So you can check the p values, you can check the coefficient, you can check the standard error. uh, huh. The p value is, that's the coefficient that is a1. Yes. So let me just use it like this. So a1 is the coefficient, and let's say wt is the multiple parameter. Okay? Yeah, yeah. Let's here also HP, sorry, then volume, then let's say SP. Okay, so let's say A1 is your parameter for WT. Now the null hypothesis is always this, that A1 is equals to 0. But if A1 is equals to 0 and that is true, what does that mean? That means this entire quantity is 0, right? But we won't want that, right? Like if if WT is actually making an impact on your y prediction, then this hypothesis should be false, correct? Yeah. If this hypothesis need to be false, p value should be less or more. Firstly, what p value indicates? So if p value is equals to 0.001, we will accept the null hypothesis or reject the null. Is the power one, right? No, the p value. You remember in statistics we calculated the p-value. So we said that what be low. Okay. So if it is low, we will accept the null hypothesis or reject the null hypothesis. P-value is low, then we will accept. Sure. Okay. If p-value is low, that means that much percent of chance that H naught is true. So for high p-value, we will accept the null hypothesis. Okay. And for low p-value, we will reject the null hypothesis and accept the alternate. Now, I think you are correct. Yeah. So if p-value is higher than 0.5, we will accept the if p-value is higher than 0.5, we will accept the null hypothesis. Okay. So if p-value is high, that means H naught is correct. So in our case, if p-value is high like this, 0.8 or things like that, then the H naught will be accepted, right? But what is the H naught? A1 is equals to 0. Okay, this is the H naught. But if that is the case, this whole term will be 0. Then so the p-value in our case should be higher or lower? The question. Low. Yes, it should be low. But see the case like this. Here, here, it is very high, right? So this is one indication that your model is having some problem. Uh, there are so there are dependent variables. You were asking, right, like r square can be an indicator or not. But see here, r square value is good, but your all other parameters are indicating that there is some problem here. And then and the p-value, if p-value is high, accept the null hypothesis. If p-value is low, reject the null hypothesis and accept the alternate. Okay. Okay, so that's the thing, and then you can just come here and come with this. Now we will check the model parameters. These are the this is the intercept value, and uh, this is the um, slope. Okay. Now we know that there are p-value indicated that there are some dependent variable. So what was our first assumption? That all features should be independent. So now we will be calculating VIF. How we will calculate VIF? Yes. How did we calculate VIF? VIF is 1 Yes, but it is the model in like while building the model, how did we build it? We build it within the features, right? Yeah, within the feature. Okay. So now we are doing the same for one, like against one feature, the other ones. And then we are calculating VI for all. Once we calculate the VI, uh, okay. So now we are calculating VIF. Once we calculate the VIF, we get these values. For HP, it is 19, WT 639, and so on. So now, are these values acceptable? What is the threshold for VI? Less than 10. Less than 10, right? So less than 10. So as it is more than 10, so we know now that it is not independent, there is some dependence, correct? Okay, right, no? Yeah. Okay, so now we will treat the multicollinearity, right? How we said we will do that is we will check all the combinations. Now from the correlation metric, I could identify that the correlation between SP and HP and volume and weight has a high correlation, right? So now I need to find out which is the uh, so you remember we identified four combinations. Yeah. Now I need to find out of these four which one is the best model. So I have calculated for one. Similarly, you calculate for others and tell me which one was the best. So just copy paste this code and just replace the this part with the second and third and fourth. Yeah. So I have shared the notebook and data um, in the WhatsApp group. Yeah, I did. Okay, so which model you found out to be best? MP volume HP. Yeah, that is the best, right? That's I tested only one. Okay. Mahesh, did you also got the same result?
No, I didn't try it.
Okay. So try it later. Uh, just try with all the combinations and just see. Okay. So a model summary, same thing. R square value we can find from here. Now check the p values. P values are 0. That means our null hypothesis is false. We will accept the alternate hypothesis, which is a good case. Like that's what we want. Correct. You can also check the number of observation here. This is the uh, degrees of freedom. Then, uh, yeah, then this is the model that we got. Now we will do the second test. Okay, we will do the test for the normality of the residuals. That means your errors should come from the normal distribution. For that, we will plot the QQ plot. Okay, this is the QQ plot, quantile versus quantile plot. You read it once. If it is not clear, I will explain it in the next class in more detail. But uh, yeah, but QQ plot, if it is like this, so just okay. So if the QQ plot is like this, on like if it's at 45-degree and uh, there is no deviation like this, can you see the tail? So all should fall if all are falling on the 45-degree line, 45, yeah, 45-degree line, then it is a it's a normal distribution. So if your QQ plot comes like this, or yeah, is a better represent. Yeah, yes. So if your graph comes like this, okay, which deviates. So this is for the normal, and if your graph comes something like this, then this is not from the normal distribution. Clear?
See the screen, not able to see. You are writing in it?
Okay.
Nice.
Can you see now? Yeah, sorry.
Yes.
Yeah. So if uh, graph comes out to be like this, so all your quantile values are falling on the 45-degree line, then this is the normal distribution. It is coming from the normal. If graph is something like this, then this is not from the normal. Clear? So as you can see here, our residual, this plot is almost falling on the 45-degree line. So we can safely say that all the residuals are uh, coming from the normal distribution, which was our assumption number 2. So now we will look at the assumption number 3, which was, there was one more, right? Let us do that. We have done it next. Okay. So assumption number 3 was the fourth one was homoscedasticity. So our variance in the error should not be changing. So variance should be constant. So what we said is we will plot the values, y bar values along with the residual values. The residue or error values that we have calculated, and then we have just plotted this graph. So between y bar and errors, as this is a there is no correlation, we can say that they are not dependent. Correct? Then look at this graph. Okay. So from here as well, here you don't, there are many graphs, but you don't need to look at others. Just one graph is required here. Look at this graph. It plots x versus residue. That means error, right? So any your feature versus the error. If this is the random scatter plot, all values are random, there is no correlation, then your assumption is satisfied. Otherwise, you will need to do the features, like, sorry, transformation. So you can see here, in this particular case, there is a some relation, right? Can you see something like a parabola? Yeah. There is some kind of relationship. So we can't assume that this is random. So in this case, we will need some transformation. So we will see that how doing transformation on this improve the model. So now we have seen all the assumptions. We have seen how to do the test. Now we will see the detecting the outliers. So we saw how to detect outliers. The best method is to find the Cook's distance. So first find the Cook's distance and find the distance. So what we did is delete, first find model with all the data, then delete one row at a time. Okay, once for all those. So So delete one data at a time. Measure the change before and after deletion. If the change is significant, then it implies that it is an outlier. If there is no significant or mild change, then it is not an outlier. Okay. And what is the threshold that we will keep? The threshold will be Cook's distance. We will be using this particular function model.getInfluence in order to calculate the distance. So this will do all the things and all the distance calculation in the backend. We don't need to do that. So we will just get this distance calculated. This will return two things. It will return the distances, Cook's distances, and p-value. As we don't need p-value here, we will use the underscore. So you usually whatever data is not important for us, we use the underscore for that particular. So now once we have all the distances, now we will plot those. Now you can see there are some distances which are for which Cook's distance is higher. Okay. So the distance is higher. Now we will check that where. So this is the Cook's distance that we found, 3 into k plus 1 divided by n. Our parameters are 2. There are 81 rows. So 3 into k is 2. and n is 81, so the distance came out to be 0.111. Okay. So then we will say find the values where c is greater than the threshold that we calculated. So it replied, like it gave us four values. Even with the graph, we can see that there are four values. One at the 70, one at 76 somewhere, 78, 79. All these values are have high, like high distance from the, um, so it this has high error. So these are the outliers. So this is how we will remove the outliers. So once we find out and remove the outliers, now, so here we will be dropping those indexes. So we will remove these outliers. These rows are the outliers that we will remove. So now we will build the model again. Now this time we will consider only two parameters, because we already saw that these are the parameters which gives us the best results. So we will be considering only these parameters. And then now uh, with with the outliers removed, we can already see quite improvement in the r square value. Earlier our r square value was 0.75. Now our new r square value is 0.84. Already it is increased quite a lot, by almost 10%. So now we can also see that our p values are near zero, so which is a good indication. So all things looks good. And then so as it is more than 0.84, 0.8, so we won't do anything much on this. So we will just do the predictions, and these are the predictions. Okay. Is this clear? Any doubt in this notebook? Anything? Any part in theory you did not understand? The predicted values, it's okay. Predicted values is just for the mileage, because what we are, yeah, we are using HP and volume in order to predict the mileage. Yeah, yeah. So what you try to do is, like you have already in the notebook for multilinear regression and SLR, right? Simple linear regression. So try to write the code without looking into this code. You can use Google, don't use ChatGPT, and don't use this notebook, and try to implement it on some other data than one that we have already uh, done or worked on. I can give you some of the some data for both. Yeah, so yeah, yes, I will put it in the classroom itself. You can download from there and try it on that. Try run like making regression models on new data, and then see how good accuracy you get. So, any doubt in this till now? Any part in the theory, assumption, test? What all resolutions that we do? How to find the outlier, and then the code part. Any part? Any doubt in this? Okay, Mahesh. Any doubt?
Fine for now. Fine.
Yeah. So today we did the MLR. We first saw the assumptions, Then we saw how to test if the assumptions are satisfied. Then we saw how to do the resolution. Then we also saw how to identify the outliers, why it is important to find outliers, and how to identify the outliers. And then we saw the code for all that. Okay. Clear? Okay, then we will wrap it up for the day. Sorry, I took 20 minutes extra. But I thought I will finish this because then in the next class we won't remember actually what we. Okay. So
Plus, if the new date,
yes, yes. I will upload the data today or tomorrow itself so that by that time you can try it out.
yeah, we can.
Yeah. Yes. Okay. Okay then.
Have a
Thank you.
nice weekend.
Have a nice weekend. Good day.
Enjoy this.
Good day. Bye.